Thank you for inviting SiliconArts to the Real-Time Ray Tracing Summit today. It's been predicted to take over the world every year for the last 20 years, I think, right?
Right.
And John, of course, has been tracking this for most of my lifetime. The beauty thing is there's a lot of great passion in the ray tracing marketplace. Everybody that I worked with and talked to about ray tracing has been basically commonly focused on how can we make it a reality. And real-time ray tracing is a particular challenge. We've seen ray tracing, surveyed by John on its use cases, even in the professional world for many, many years. But gaming, I think, is an enormous market that everybody's really interested in getting that kind of realism, especially when they're consuming high quality content video. They want their interactive games to have that same kind of quality, right?
Right, exactly. Yeah, exactly.
So
I'm going to mute myself here and I'm going to let you take over, okay?
Okay, very good.
Right.
Well, I think that the benefits of ray tracing have been covered, in the previous presentation. So I won't go into great detail, but understanding the four major effects of light: reflection, refraction, transmission, and shadow, are all able to be incorporated in ray tracing. And the photorealism, I think, is what everybody's been focused on and talking about. But some of the other advantages is that it's actually a lower production cost and maybe shorter lighting development for photorealistic effects than using conventional shading. Rather than using an artist brush, you just use physics to create that. So it's very reproducible. And the screen independent the format is independent of the screen size, so you don't have to worry about how you're going to fit into all the different kind of screen sizes based on the geometry engine that you're driving. And there's a lot of commercial opportunities in the high quality contents market for this. I think we've seen applications where with the photorealism, it's applied into enterprise and VR use cases, which would be considerably like enterprise, but they're applying games to them. There's a great example of a VR program that wanted interactive graphics used to train medical personnel, and the photorealism was really important so that it was actually going to work properly. And if you look forward, VR is really going to need ray tracing to create effective immersion. If you start diving into a VR environment, if you've ever used it, as John said, the artifacts become particularly bothersome to your consciousness on whether you're inside the game or not. So we're going to see it adopted. The question is how do we make that adoption happen broader? So Rasterization GPU, this is the industry for the last 30 years. It's got a tremendous set of benefits, solid cross-platform APIs. Kronos has done a fantastic job there. Advanced design tools, well-honed methodologies by all the gaming creators, optimized gaming engines with full features, and then the content creators themselves have great skills using rasterization graphics. And I think this is a key point, is that as developers learn how to use ray tracing, it's going to have a significant impact on the deployment of it. Having hardware or software that does ray tracing isn't important if the people developing the content can't take advantage of those properly. And it's a good to basically take a look at a lot of the materials that NVIDIA has put up, because they've been an industry leader here and showing a lot of the kind of techniques and skill sets that apply not just to the NVIDIA platforms, but ray tracing in general. And we know the limitations on realism, shader development, and the screen size, but ray tracing has a lot of GPUs. Ray tracing GPUs have a lot of challenges, and part of the adoption has been a combination of the lack of a target, real-time ray tracing targets to run things on. As John said, you can do it on a CPU, but it's very, very slow. And real-time ray tracing really has not been possible on targets until very recently with some of the new platforms that have been put out there. The other challenge is legacy raster content support is also required. I mean, ray tracing does not replace raster graphics. It might in the longer term, but since there's so much skill sets, content, and tools for rasterization, it's not going to go away tomorrow. And that means you have to coexist at your real-time ray tracing capabilities with the raster ray tracing capabilities. And then, of course, the development tools and skills for ray tracing are not comparable as they are for rasterizing. And we need newer and updated RT API extensions with the current graphics APIs. So these are still being finalized. And I think, as Neil correctly said, without that finalization, you're going to see reluctance of developers to pile onto that platform. And of course, there's limited player hardware platforms to support RT. I think that we looked at NVIDIA on the PC is the real full-fledged ray tracing platform that you can use today. And how do we support other platforms that don't have that expensive latest generation GPU architecture on it? And I think that the presentation from Adshir is a good example of techniques that are looking to address that challenge as well. So I've kind of covered these. So let's go to where I see is we're quite excited. Ray tracing is coming to games in 2020. I mean, we saw the release of Minecraft with ray tracing from Microsoft just in April, and that was, of course, on the PC platform. And then we're seeing 2 consoles being released with ray tracing, both the PS5 and the Xbox X, with AMD-based ray tracing hardware on them. So developers are getting new ray tracing tools, APIs, and material libraries as well based on this. So this really creates an environment where now the developer has an incentive to create ray tracing content, at least if he wants to support at the high-end PC or these 2 game consoles. So the question is, how does ray tracing come to more games, right? Beyond a PC that has a dedicated GPU card, or you buy the latest generation console. And I think that there's a whole sequence of areas. I've kind of listed all of the ones that we see here and try to describe each one of those. The first one is hybrid content development. And you're actually seeing this today. Pre-baked ray tracing scenes for high complexity lighting scenes are used. So you're actually not actually doing real-time ray tracing. You're actually adding static ray tracing, and then it's overlaid with in the raster environment. This is effective for maybe far scenes, but when you have interactive scenes, it really doesn't provide that. So it's a bit of bling in the background, but it doesn't really provide the RT gaming and RT lighting advantages in an interactive environment. The other is to overlay RT shaded material segments and objects in a raster scene. And this is actually what we'll see a lot of. This is part of, I think, some of the demos you saw in the ad shares is that you have a rasterized image, and in those areas where materials have particularly complex reflection or lighting structures, that you actually segment those out and you utilize ray tracing for those segments, and then you integrate those together. And then finally, we see ray tracing deployed in the cloud to do real-time global illumination computing. I think it was disclosed at Beat Games earlier this last month that Amazon streaming games is actually deploying global real-time illumination in their cloud game streaming environment. So this is an advantage because you now don't need the RT hardware in the client to deploy it on a game, so it can be very rapidly developed and deployed. All you have to have is a client that has enough bandwidth to support the streaming situation. There's hybrid software, real-time ray tracing processing. This is software emulation of ray tracing on an existing shader GPU. So that was really pioneered by NVIDIA with the optics solution. And AdShear has basically described that with additional optimizations and to contain improve the parallelism that can be computed on an existing shader architecture by grouping them together. And then, of course, that requires a library for each target GPU and a trade-off complexity, because when you're using the shader GPU for, of course, ray tracing, that memory is not for rasterizing, so you have to focus on managing, your memory utilization when you combine those. And then there's hybrid GPU architectures themselves, and I've grouped these into two buckets. One is ones that or hardware acceleration on the CPU for accelerating the dynamic scene management. And this is essentially doing the bounded volume hierarchy calculations to identify what to compute. Your rays are going to scatter all over the place, but you only need to compute the rays that the viewer is going to actually see the results of. So you're really, if you had to compute all the rate bounces of a lighting scene, it could be phenomenal, except you realize your field of view is going to limit which bounces that you're actually going to see. So you only want to compute those that come into the field of view and limit all the rays that bounce outside of that field of view. Those are typically done on a CPU, and if we bolt a ray tracing accelerator for these types of calculations, that can significantly improve the performance in that area. And then finally, on the GPU, on the actual ray tracing dedicated engines, this is utilize a ray tracing accelerator to offload those actual ray tracing compute functions from the shader engine. So the shader engine can focus on the shading, and then you have a dedicated element to do the ray tracing. In fact, these are often combined in the current GPU manufacturers. They combine these engines within the GPU. If you look at like if a Turing or the whole sequence of NVIDIA architectures, they've been adding RT accelerators within their overall GPU architecture. And that's allowed the industry to move forward, because now they've given an integrated platform that supports all the legacy raster features and all the new ray tracing features there. And then both in the approach that they take and others take is that you can integrate these ray tracing shaded segments with the raster shading using compositing, which is basically, if we take a look at this, is we take the last pass, we basically have a ray tracing GPU architecture that's doing ray tracing generation, traversal intersection test, and shading. And that's actually mapped in the final pass with the rasterization GPU. The effect of this is that since every pixel on the screen is not being computed with ray tracing, you need less rays per second to compute. And the rays per second is the benchmark that people look at for the computational performance. Now, when we looked at the new consoles coming out from AMD, the PlayStation, and that they said about 10 teraops of teraflops of computation to perform the ray tracing functions. But that really is computed down to how many rays they generate per second. Now, since these are generalized processors, every teraflop is not directly computing an RT function. There's some efficiency there. So what you'll see is that you want to have almost an infinite amount of ray tracing computing elements, and you have to basically scale it to what's available on your hardware platform. That's why I think John said, no matter how many computing elements you have, ray tracing can consume those. So what we need to do is match up the content rays per second that we need with the target platform's capability to deliver those. And by using an overlay, we can say we're going to use a lot more rays for the scene than we would if we had to compute the entire scene with ray tracing. And that allows us to focus the ray tracing benefits on those materials that really need realism. And then we can do parts of the scene that don't require that with the rasterization GPU. If you have a static image and the eye is allowed to look at it for seconds and seconds, you can build a great amount of information, but in a real-time gaming environment, it's not necessary to have that level of deep shading for every image, but it might be on the screen for fractions of a second, where the eye really doesn't get a chance to absorb the detail that's shown there. So what we see is a hybrid development approach where the gaming community is still going to be centered on raster graphics for development for gaming. I mean, you're going to use existing developer graphic engines for content creation, like a Unity or Unreal, and then you're going to use raster lighting for a majority of the scenes that are involved in. And then when you augment that with ray tracing, specifically for those materials lacking in realism. If you looked at like the pictures, you might have a reflection in glass or through water. Those materials would use ray tracing, whereas some of the conventional materials that are in the scene would not require that. And then finally, you can use the final lighting pass for compositing these together. And of course, the game engines are extending those so that we can basically use a game engine API to integrate those together. So SiliconArts RayCore architecture is really partitioning the ray tracing problem into those two areas. The viewing port, what to compute, which is the bounded volume hierarchy calculations. And those are traditionally done on the CPU. So we can do a coprocessor that can vastly accelerate those. Most servers look at doing this with an array of maybe, a cluster of CPUs, 16 CPUs, whereas you could maybe tie a coprocessor to a single CPU and perform the same kind of performance. One of the ways that's done is if you look at the processing, you have some working memories that if you relied on system memory or the high-speed buses to perform this, it becomes a limiting factor. It's not just the computations, it's the accesses to the models and the memory that can limit you. And then finally, the other half is a GPU coprocessor that is actually computing the actual rays themselves, and that kind of is a coprocessor to the legacy GPU. So this is, if we look at breaking the problem down in these two ways, we can come up with a hybrid client CPU GPU architecture diagram here, where we have of course, your 3D game applications, your game engine on a particular platform. We utilize either a DX or a Vulkan type of API, but then you have a ray tracing API extension. And then the ray tree, which is the BVH computation, can work directly with the CPU to compute those functions and then pass those off to system memory to the legacy GPU and the RayCore ray tracing GPU to actually compute the rays that are needed in those segments that are identified for that, and then integrate those. Now, this provides us a way to take platforms that are available today, whether they be integrated platforms or lower or middle performance GPU platforms, and provide a capability to run ray trace enabled games on those platforms. Now, of course, these require hardware changes to the target platform, so it's not going to be adopted in the near term. Software we would expect to be adopted sooner, but we're also seeing cloud-based ray tracing to be being adopted as well. Ray tracing in the cloud is really a natural, since the dynamic scene viewing port can be computed with a very large model hosted on the cloud. Multiplayer environments can deploy complex scenes for a composite scene representation there. And that lighting model is an extension of that 3D model that is already developed there. And then this ray tracing GPU performance is not required for all the players to have to join this if some of this computing is done in the cloud. So then the question is how can games utilize the cloud? So clients with limited or variable network connections can leverage basically a client render acceleration with the hybrid RT GPU, where in those functions, only the BVH calculations or the front end, the adaptive scene calculations are done in the cloud, and then they can send down commands to the client to do the actual ray tracing calculations. And then you also see solutions where clients with high bandwidth, network bandwidth performance can utilize complete cloud rendering to reduce the dependence on the client ray tracing GPU capabilities. So we can see this happening quite faster because you don't have to replace the clients with new hardware. And you'll also see it used in combination with maybe software RT clients like Azure described as well, where you can split the problem in cloud acceleration for the adaptive scenes portions, and then use software libraries on the client for the Ray's performance. So this would give you a view of basically taking our technologies and splitting it between those two, where we actually take the CPU coprocessor, and that's actually delivered on the cloud as an accelerator to the CPU, as a PCIe Express card, or even integrated into an ASIC in the cloud. And then on the client side, we utilize the RayCore GPU processor to do the actual ray generation, TNI shading, and texture mapping. And then this would require some kind of sharing with the shading interface to integrate those images. So I think, in summary, I think ray tracing is now will be a clear focus for gaming developers. And then the question is, how are they going to go about it? They're going to, game consoles and high-end PCs create that demand. And also real-time ray tracing can be deployed in the cloud today. So I think of the challenges that we see are being addressed, there's new support seen in both the developer tools and ecosystem expansion. So that's really been one of the limiting factors. There's been no content. The standards, the legacy IAPI extensions for ray tracing are being improved now, as Neil has described, and SiliconArts is joining Kronos to support those RT extensions. We think those are very important for the industry to move forward. And then on hardware platforms, the approach is to emulate ray tracing on existing hardware platforms, these new platforms we're seeing out, and then some of the hardware approaches we described today, splitting the efforts between the cloud and the client, can address both mobile and VR use cases as well. So I have a little demo here. I'll show of what let me see if I can share it. Let's see. There we go. See if I can get the cursor out of the way. There we go. This just shows a high reflectivity that you get, and this is actually our Monte Carlo path tracing core, where you can see the soft shadows under the chair, transmission through the gate. So you get both the reflectivity and the transmission. And here it shows up to 13 bounces off the windows here. So that's another issue of, the complexity that you want to incorporate. So that was kind of my summary there. See if anybody has any questions.
Hi, Steve. Someone said that the video didn't display for them. Maybe do you want to just try running it one more time?
Sure. Can we see the screen now?
I can see it, yeah.
Okay. So here you see reflections of the walls, the windows, and the floor. So there's water, and then there's highly reflective glass, and the combination of those with soft shadowing, transmission on the gate, and then we can see multi-bounce reflections to the windows up to 13 times through. And this is actually our path tracing core as opposed to the ray tracing core that we offer. We see ray tracing probably the initial application on gaming, and then path tracing is extensively used in the movie visualization business, and we'll see that actually as a roadmap in the future for gaming as well.
Great, great. That came through. I think there's a question. Does RayCore run natively on existing hardware?
No, RayCore is actually a hardware core that it offloads the ray tracing computations from the existing GPU. So it requires integration in silicon. We do actually have a silicon device that has a USB port. We can actually plug it into like a Mac or a PC and utilize that to offload, but you're going to not get the full benefits because you're going to have the limitations of the I/O between the external device and the platform itself.
Okay, great. Let me see. I think that was the only other question. So we've got, yeah, that was the only other question that we had. So thank you so much. That was really interesting. Great. It was a great presentation.
Well, thank you.
And thank you so much for joining us.